Now that I've told you what Newton's second law is, it's time to see it in action a little bit with some problems. A classic example of this, and one that I see a lot of test problems on, is a man in an elevator and what the forces are on him when the elevator is going up and down and that sort of thing. So let me sketch this out for you. So here I've got my guy and he's just hanging out in the elevator, and we're going to draw a whole bunch of different situations of what the elevator can do while he's standing there. I'm sure maybe when you were younger, or perhaps even now, you've spent some time in an elevator going up and going down, and it felt kind of weird, right? We're going to talk about why. But anyway, this guy is 60 kilograms to help us figure out exactly what the forces are going to be on him. So let's get some situations going. So in the first case, let's just say that the elevator remains motionless and we want to find out what the force diagram is going to be on him. It's the same process we've been doing. If the elevator and the man stay motionless, then Newton's first law says that the forces must be in balance. And there's always going to be a force of gravity on you. It's just 10 times the mass. So if he had a mass of 60 kilograms, then his force of gravity is 600 newtons. And there would have to be a normal force of 600 newtons as well. In this case, the normal force simply means how hard the floor of the elevator is pushing up on the guy. So if you were to stand on a bathroom scale and you have a weight of 600 newtons, then the scale would read 600 newtons. So this is a pretty boring situation, but they'll get a little more interesting. For this next one, he presses the button for maybe the third floor, and the elevator all of a sudden starts accelerating up. The elevator was at rest, but all of a sudden it's moving faster and faster and faster. And you've been in an elevator before, so you've felt this, right? How do you feel when the elevator suddenly starts going up? Well, you feel heavier, and we're going to show why the forces do that. So we begin with a force of gravity of 600 newtons, no surprises here, but the normal force is going to take a little bit of calculation. If we use Newton's second law here, then we show F net equals ma, and in this case we know mass and acceleration. The guy was 60 kilograms and the acceleration was 1.5 in the upward direction, which gives us a net force of 90 newtons. So in this case, the normal force is equal to 90 newtons. I hope you were paying attention, because what I just said is wrong, and it's a mistake I see a lot of students make. The normal force here is definitely not 90 newtons. What I said is that the net force is 90 newtons. So we can't just throw a 90 there. What it means is the leftovers, the extra force that's left over at the end, is equal to 90 newtons. This is the correct way that you use that information. You would say that the normal force is 690. In other words, if he were standing on a bathroom scale, what a bathroom scale reads is your normal force. It tells you how hard the scale has to push up on you. And when an elevator all of a sudden starts going up, you feel heavier. And the normal force is what describes how heavy you feel, not the force of gravity. So this force diagram shows a net force of 90 in the upward direction, which explains the acceleration on the man. I'm going to start going a little quicker on these. On this one, the elevator simply goes down at 3 meters per second. And in that case, it's not accelerating, it's just going at a constant velocity. It actually turns out this is the exact same answer that we got on the first one. Because if he's going at a constant velocity, there's no acceleration, and if there's no acceleration, then the forces are in balance. And you've felt this before, right? You only feel heavier or lighter when the elevator changes its velocity. If it's going at a constant velocity, it doesn't matter how fast it's going up or down, you can't feel it. You feel the same as usual. So the forces are in balance. They're just like if the elevator were at rest. This next one says that the elevator now accelerates down at 4 meters per second per second. And as you've probably felt before, when the elevator suddenly starts going down, you feel lighter. Using Newton's second law, we find out that the net force on this man's body is 240 newtons. But the way that that plays out in this one looks like this. In this case, that net force is pointing down, which means the normal force has to be 240 weaker than the force of gravity. So you get a normal force of 360 newtons. The guy doesn't feel as heavy anymore. For this last one, the man actually brings his own bathroom scale on board, and the bathroom scale reads 800 newtons, even though he's only a 600 newton guy. And we want to know what's the acceleration of the elevator based on that reading. In this case, the reading on the bathroom scale tells you his normal force. So the force of gravity on him is 600 newtons down, but the normal force up on him is 800 newtons to produce that net force. If I run Newton's second law on this, I get 200 equals ma, and then a is equal to 3.3 meters per second per second. And what direction is that going to be? Is he accelerating up or down? Well, if he feels heavier, if this normal force is the one that's stronger, that acceleration is going to be in the upward direction.